are the homework solutions to the linear motion problems. I'm just showing you one way, maybe occasionally two ways to solve these, but in reality, there can be many ways to solve them. So you just want to be thinking about what mathematical formulas you might use, why you would use those, make sure you're not plugging in like a velocity into something that's really supposed to be an acceleration, or an average velocity into a final velocity, or things like that. So going ahead, PC 24, this is asking you to figure out how far something goes when you know the acceleration and the time. So I would use something like that. That's a version of Formula 4. I'm going to come up with 47 meters. For this one, the first thing we've got to do is figure out how far we're going. So it says it's a quarter of a mile, 1,609 meters per mile. So that's 402.25 meters. Average velocity, change in position over change in time. So we get 90.7 meters per second. I initially thought it was asking the final velocity first. It was not. It's asking for the acceleration. So you could think about trying this, which is change in velocity over change in time. But what happens is a lot of people try to use this, and they put in 90.7 as the change in velocity. But that's not correct, because the object starts at 0 meters per second. Its average velocity is 90.7 meters per second. So its final velocity would be much higher than this. In fact, double this. So unless you know that final velocity, or you know that that allows you to figure out the change, you can't really use this. You could use Formula 2 to figure out that final velocity, but again, for most people, what they would probably do is use this again, rearrange it to solve for acceleration, because many times what we want to do, things are not solved on the left-hand side properly. Or the variable we're solving for is not just all by itself on the left side, so you have to rearrange it. So rearrange that, got around 40.9 meters per second squared. For this one, again, there's other ways to get this. You could go back and use this formula or a version of that formula now. I chose to use this, which is Formula 5. So I know my initial velocity is 0, so that makes that easy. 2 times the acceleration I just found out, times that change in position, which was given. I end up getting VF squared is somewhere very high. Take the square root of it to get around 181 meters per second. And notice this is double the average velocity. For 13, I asked you to use the graph, so I want you to be able to use both things that are graphical methods of solving problems as well as calculation methods. So with this, you're asked to find the acceleration. That's simply the slope of a velocity time graph. Don't know why I didn't put the parentheses on the other side of that, units for meters per second, but oh well. So that slope, position 1, position 2, so 0 minus 18 meters per second, 6 minus 0 seconds. And that's an acceleration of negative 3 meters per second per second. To find the distance you travel, in this case we get the area of this graph. That's 1/2 height times base. 1/2 18 times 6 is 54 meters. For PC 18, this is a plane, and it needs to reach a takeoff speed of 28 meters per second, and it can accelerate at 1.9 meters per second per second. And you're asked to figure out the length of the runway. So there's a couple ways you could do this again. You don't know the acceleration because we don't know the time it takes to take off. So that kind of limits you from using formulas 3 and 4. So I'm going to use formula 5 here to figure out this distance. So final velocity is actually 28 meters per second. People might think that's the initial velocity because that's the takeoff speed. We're talking about the plane gaining speed on the ground. So it starts at 0, ends at 28. That's the acceleration times 2. So I get 28 squared is equal to 3.8 times delta x. And so that delta x is 206 meters. That's about 650 feet. That seems very short, but honestly for a single engine plane, small plane, that's not that unreasonable. So again, there's other ways you could do this. For example, you could have used this to solve for time and then plug time in there. For 20, we have someone who's skiing. I'm tired, pardon me. and they're actually slowing down. And so it's appropriate since we've had the Winter Olympics going. So they're starting at 29 meters per second. They finish at 1.8 meters per second. That takes them 1.45 seconds. That is a very rapid negative acceleration. So use this formula, which is a version of Formula 3. Get an acceleration of negative 18.8 meters per second squared. And to figure this out, you could use another version, a version of Formula 4. I have to use this longer version because I do have an initial velocity. So initial velocity times time plus 1/2 at squared. Notice the initial velocity is positive, the acceleration is negative. So I get about 42.05 meters minus 19.72 meters. So I get around 22.3 meters positive as my displacement. 28, you've got a camera. The person's reached a terminal velocity, but then they drop the camera. So actually this 10.4 meters per second is at the initial velocity, and it's dropping 52.1 meters to the ground. Hopefully by now, this time of the year, you know the acceleration due to gravity is 9.8 meters per second. So again, I'm going to use something like this. I'm just showing delta y instead of delta x because this is a vertical problem. So I go get that, rearrange it, get a final velocity of 33.6 meters per second. To figure out the time it takes for it to hit the ground, I'm going to use Formula 3 here. Rearrange that to solve for the time interval because I know that for every second, the object is speeding up by 9.8 meters per second every second. So that's around 2.37 seconds to hit the ground. PC30 is actually something, I think I showed the video of the feather and the cannonball, hopefully I did, in free fall. And those are going to accelerate at 9.8 meters per second squared. The distance before the braking is 132 meters. So again, I'm going to use this. I'm just using delta y since it's vertical, no worries. So it's around 5.2 seconds. To find the final velocity, well, you're increasing by 9.8 meters per second every second for about 5.2 seconds. So that's somewhere around 50.9 meters per second. Problem 8 will probably go over in class, but it's actually super useful because there's some symmetry. So in this case, you know very little information. The only thing you're given is that Braden throws a ball straight up and it takes 3.56 seconds to come back down. So I'm assuming this rise and fall is the same height. So either he's throwing it from the ground level and it's hitting the ground, or he's throwing it from his arm and it goes back and he catches it in his arm. But this is all the free information we have. So you should know that the time up is going to be equal to the time down, and that's equal to half the total time in the air. Why? Because gravity's slowing it down on the way up and speeding it up on the way down. You should know the acceleration due to gravity is 9.8 meters per second every second. You should recognize at the tippy top, the velocity is 0. Why? It's not moving up and it's not moving down. And so, due to symmetry, since gravity is acting against the object's motion moving up and with the object's motion moving down, the initial or the thrown velocity should equal the final velocity as it's caught, just in the opposite direction. So to do math on these, it's usually easier to think of half the trip than the whole trip. Because oftentimes if I think about the second half of the trip where things are coming down, my acceleration points down, my velocity points down, I don't have to worry about combining positives and negatives. So because there's symmetry in this half of the trip and the first half of the trip, a lot of times I can use that. So for part A, it's asking the speed with which it's thrown. Well, the speed with which the ball is thrown is the same as the speed at which it's caught. So if I think of the second half of the trip, my initial velocity up here at the tippy top is 0. It's accelerating at 9.8 meters per second every second for 1.878 seconds where it's falling down. So that means it's caught at 17.4 meters per second. So the throw is 17.4 meters per second. To figure out the maximum height this rises, well, the easiest way to do that is to think about the second half of the trip also, because the height to which it rises is the same as the distance at which it falls from the maximum height. So for me, it's going to be easier to think of the second half of the trip. I know my initial velocity at the tippy top is 0 meters per second. I know the time it's falling is 1.78 seconds. And I know that the acceleration is 9.8 meters per second squared. So I can use this delta y equals 1/2 at squared. I know my acceleration due to gravity. I know the time it's falling. And so that ends up being a 15.5 meter distance. And so that's the maximum height. Now, you could also think about this with the first half of the problem. But because there is an initial velocity here, and the final velocity is 0 here, I would need to think about that as having an initial velocity up, so I'm going to call that positive, and it's going up for 1.78 seconds, plus 1/2 times a negative acceleration times 1.78 seconds squared. So if initial velocity is upward is positive, then my acceleration is downward, and that has to be negative. You could flip-flop these, but your goal is to find the maximum height, and so that's really kind of an absolute value, whether you come up with a positive or negative 15.5 meters. But when you do this and you have objects going different directions, you absolutely have to have your signs correct. So positives and negatives matter here. Whereas here, we don't really need to worry about it. Hope that helps.